All right, so I guess this will just be a review for one student who sent me questions. So we'll take a look at those. So first question I had was, I mean, I'm doing these out of order, I suppose. On the IR spectrum 3. All right, so we're going to take a look at that. So when we're looking at IR, remember the only thing that we care about is functional groups and where those are located. So this spectrum, we should see two peaks of interest. We see that we have this broad thing between about 2400 and 3400 or so. That's pretty indicative of a carboxylic acid, right? That's indicative that we have that super broad bird wing type structure there. That's a carboxylic acid, and we have confirmation of this in that we have also a carbonyl peak at around 1700. And so those are the two indicators here, and so we're going to say that this is going to be a carboxylic acid. Remember that for this sort of thing, it's kind of terrible to make that determination of what it is, but this has to be H. Like, it's since you're given options here, it's usually IR is not enough to tell a full structure, but if we're just comparing something, the only carboxylic acid is H. And so that's going to be our answer. It's the only thing that has the bird wing, so the giant, broad, with little tips from the CH bonds, and then it's also got the carbonyl. So it's got to be the carboxylic acid here. All right, so remember, that's what we're looking at with IR, so good stuff. All right, let's take a look at reactions module question 8. Okay, reactions. Question 8. All right, methyl cyclohexane is brominated via free radical reaction to produce mixed isomers, blah, blah, blah. Draw all of them. Oh, that's fun. And then indicate which ones will be major. And then we have some other stuff. Okay, so let's go ahead and take a look at that. Welcome, whoever just decided to join. Yay. Okay, we'll take a look at that one. All right, how's it going, Shane? I am currently doing the radical reactions number 8. This is a question that was asked outside of this. Oh, you're like free to talk, by the way. You don't. It's not just me. So, okay. But we'll go ahead and take a look at this. So we have methyl cyclohexane being brominated. So really, we're looking, if we're supposed to draw all the bromination products of this, everything that's possible, we just have to stick a bromine on all the different spots, right? So let's go ahead and do it. So we can stick a bromine on here. That's going to be our major product, right? And we know this because bromine selectively will choose a tertiary spot over others. So everything else will be a minor product. We can brominate on the primary carbon. We could brominate one carbon away. And we can brominate 2 carbons away from the methyl. And then we can brominate 3 carbons away. And all of these would be a mixture of stereoisomers as well. Depends what methyl substituent we had. Like if that was if it's a wedge or a dash, that may change things. So we're going to have a mixture of isomers, of stereoisomers, but these would be all the constitutional isomers that we would have. So where we have the same things but different kind of connectivity. So that would be the 5 products we get out of this. So that's 8A, I suppose. 8B is using the Hammond postulate to explain why the major product prevails over the others. So our major product is this one, right? Where we have the bromine on the tertiary position. remember that the Hammond postulate is asking us to describe the transition state. We remember that bromination is endothermic, unlike chlorination, which was exothermic. An endothermic reaction, this is also a two-step, right? We end up having the radical as our intermediate. So we have an endothermic first step, and then we have the kind of exothermic last step for the bromination process. So, but if we're looking at just the radical being formed here, it really, let's go ahead and look at the, in either case, right? So let's take a look. So here is our intermediate. That's the radical. And we can look at both the transition states before and after this radical is formed. We see that this hump on the left shows an endothermic part. I'm going to just eliminate this because that's just going to confuse us, I think. We have an endothermic first step and we have an exothermic second step, right? We have bond breaking, which is always endothermic, and then we have the exothermic one. Remember that endothermic, the endothermic step, always the transition state looks like the product, and the transition state for an exothermic reaction looks like the reactant. And so in either case, we're going to see that predominantly speaking, our transition state is going to look more like this radical than either the hydrogenated or the brominated species. So we're going to see that the transition state for forming the radical will look like this. That'll be this first kind of step. The transition state for the bromine coming in also, again, will look more like the intermediate than the product. And so in either case, our transition state in both steps will resemble the intermediate. Which is the radical. And so if we want to talk about why we get this as the major product, it's because that tertiary radical is more stable. Since this thing is going to spend most of its time looking like the radical, the more stable that radical is going to be, the longer this thing is going to last, and so therefore it's going to be able to react to get to our product. So the idea here is that we're showing that because it's going to spend a lot of the time going through this transition state, the more stable we can make the transition state, the better it's going to be. So we want our radical to be the most stable. So our transition state for the major product should be the most stable of all of them. If we take a look at some of the minor products, we see that we have secondary or primary radicals. Those are not as stable as these tertiary ones are. And so as a result, because it's going to spend time hanging out like this, the more stable we can make it, the better. And so that's why we see that huge proportion of bromination products being tertiary, right? 1600 to 1 for primary versus tertiary. Or 84, 83 for secondary. So remember, that's about the 82 to 1600, something like that. That's primary, secondary, and tertiary for bromination. because that transition state hangs around so much longer, because the intermediate is so important there. Remember with chlorination, it's like 1 to 4 to 5. Not really a huge benefit there, because for chlorination, it's exothermic for both, so we end up getting the transition state becomes less important than it does for the bromination. Okay, so that's the part B, and then if we want to calculate delta H for this, we have to consider that we are breaking this bond. We are breaking a Br-Br bond. We are making an HBr bond, and we are making a CBr bond. So we are breaking a tertiary CH bond and a Br-Br bond. So we're going to use those as positive values. And then we are making a CBr and an HBr bond. And so those will be negative values. And I don't have these in front of me, but I suppose I could look them up. All right, give me a sec. We'll look these up, these values, and then we can get the actual numbers. Okay, what chapter is this even? I know the book has all the bond enthalpies. This is chapter 10. Okay. So a tertiary one is 381. A Br-Br. Where the heck is this? There it is. Okay, so a Br-Br is 193. CBr will be 293. Although that's technically a primary, well, whatever. And then HBr 368. So we're taking 381 plus 193 minus 293 minus 368. Thereabouts. Let's do the calculation. 381 plus 193 minus 293 minus 368 equals negative 87 kilojoules per mole. So I, of course, would provide you those values if I were to ask you something like this. So there's no need to like have to memorize those or look them up or something. So, all right, so that was 8. And then, Shane, I've got one more question from Gurpreet, and then we can have some of yours, if you like. This is spec practice problem 2. Okay. Let me pull that up. Okay, so, how will I do this? First, let me write the formula, and then we will try and figure out how to do this. Okay, anyways, for number 2, the formula is C4H8O2. All right, and so let's look at the spectra. Okay, so for the spectra for number 2, I'm gonna put those into my recording area. So, and I guess Shane, since you're watching my screen, here, I will switch screens for that. Okay, so that should switch your screen, so we should be on this now. All right, so looking at, awesome, okay, good. So if we look at the IR data we have here, the only thing of interest that we see really is this peak here at 1728.44. That's a carbonyl of some sort, right? So that's really all we're getting out of this. We just see CH at 3000. There's nothing, there's no blobs. So we don't have any OHs. We don't have any carboxylic acids out here. So we have only the carbonyl there. So if we take a look at like our work, let me switch back to here. So IR tells us we have a C double bond O, and we have no OHs, right? Because if we did have OHs, we would see those at 3,000 thereabouts. We would see a blob. So that tells us, because we have two oxygens in this molecule. By the way, we should do the IHD. Let's do that first, actually, before we even look at the IR. Let's do the IHD. That's always something we should do first. So that's carbons plus nitrogen over 2 minus X over 2 minus H over 2 plus 1. So that's going to be 4 minus 8 over 2 plus 1 equals 1. So we have one double bond in this molecule. And since we know our IR shows a carbonyl, that's where that double bond is. So we have one double bond. That we know from our IHD, from the formula. All right, so because we have two oxygens, we either then have an ester or a aldehyde ketone plus an ether. Those are your only two options. So remember, an ester would be like that. Something that has an aldehyde and ketone and an ether might look something like that, right? Where we'd have two different bits. We would have an aldehyde or ketone plus an ether. We don't know quite yet, just from the IR, but all we know from the IR is there's no OH, and we do have a carbonyl. So we have to then look at the rest. So the idea here is that we figured out now some bit about this. We either have an ester or we have a ketone and an ether. So we don't know yet. We can figure that out, hopefully, by looking at the rest of our spectra. So let's take a look at the NMRs. And let me move this one down just a little bit so we can see the scale. All right, and Shane, I'm going to switch this back to the other screen now. Okay, so now we should be looking at the NMR. Okay, so with the NMR, we have, I'm going to just write these down. We have a singlet at about 8.1, I suppose. That's integrated for 2.2. At about 4. We'd say that's 4.15 or so. We have a triplet. And the integration is 41.6. And then at 1.7, we have, what is that going to be? Probably a sextet, I would say. Because we have two big ones in the middle, two on the side, and then we have these very tiny little lumps. So it's probably a sextet. We might just say multiplet because there's some weird stuff going on there. It could be a quadruplet, or it could be a sextet. One of the two. And then the integration is 44 for that. And then the last peak we have is about 1.0. We have a triplet, and the integration is 67.0. All right, and then carbon NMR, we have something at 160, something at 65, and then like 10 and 20. So we have 4 peaks there. All right, which makes sense because we have 4 carbons in our molecule. So we have no symmetry. That's another part we get from this. Okay, so switching back. So this is the information I've taken from the NMR. So we have a singlet at 8.1. We have a triplet at 4.15. We have a sextet or a quadruplet at 1.7, and then we have a triplet at 1. And so let's go ahead and figure out these integrations. We can probably see these are all multiples of 22 or thereabouts. So this is probably 1, 2, 2, and 3. Again, if you wanted to be super more precise, you would divide them all by 22.2, and you'd see, yeah, it's pretty much a 1 to 2 to 2, 3 ratio. And if we see that adds up to 8, and if we look at our formula, indeed we have 8 hydrogens, so this would be the correct ratio. So singlet way up there at 8.1, we really only would see 2 things way up there. We either see aldehydes or carboxylic acids, and carboxylic acids really are 10 plus. So a singlet way up there worth 1 proton is usually pretty indicative of an aldehyde. And indeed, this is confirming because we have a peak in our carbon NMR that's up there in the carbonyl region. However, we don't really see, so aldehydes, remember, we expect them to be about, 200 in carbon NMR. So we have an aldehyde in the protons, but this is not an aldehyde. So what do we do with this? Well, consider we had either aldehyde, ketone, and ether, or an ester. And remember that this would be something more like 160. That's going to be non-aldehyde, non-ketone. So that tells us we no longer have this as an option. We have to have the ester. And so, because we know we also have an aldehyde in here, we know that we have an aldehyde ester. We know this because we would expect, if we didn't have an ester, if we had just a pure aldehyde, as in we just had a carbon on the other side of that, not an oxygen, we would see that in carbon NMR about 200. Even up to 220. Quite a bit higher. We see that non-aldehyde ketone carbonyls show up between 150 and 200. So that would be carboxylic acids, esters, amides, acid chlorides. Those all show up lower than 200. So we now know we have some of our molecule. So we have this part so far. So we've taken care of 1 carbon, 1 hydrogen, and both oxygens. So far, so good. Since Shane, you're the one here, I'll go for feedback from you. Does that make sense so far? How we've figured out that we have an ester on the other side of our aldehyde?
I mean, theoretically, yes. It's just not as easy for me. Like I don't have these the where in the scale everything is memorized.
Okay. Well, I would have a chart out. Because yes, obviously I'll be able to do these faster than you guys would, right?
Where could I find that chart?
I think Kevin posted one. Let's see. But it'll be a while ago. Let's scroll up and find out. Because it'll be definitely valuable to have that. Having reference values is always nice. Okay. Where did he put this? Blah, 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 blah. Wow. I'm going really, really far back. Oh my gosh. When did we even, first start talking about this?
I don't know. It seems
years
ago.
Time ago. Yeah, it does feel that way. Was it after? It was after SN2 and all that, right?
Yeah.
So, okay. Well, in that case, let me just Google one and I'll just post it for you. Okay.
Yeah, I don't remember that kind of chart being posted.
Maybe I'm just crazy. So, chemical shifts for a proton NMR. Here we go. Here's one. Although it's probably going to have a bad background, I'm going to put it in extra resources for you guys. Yeah, the carbon. Okay, let me find a better one. All right, let's try this again. That's better. Let me delete the other one. So take a look at that. So that's what we're looking at for Proton NMR. Okay. These are kind of variable ranges, but it may be worth it also to just kind of make your own chart for the kind of values we talked about in some of those lectures. And as for carbon NMR, we can go ahead and get one of those as well. Okay, and then here's carbon. Okay, so carbons, so that's the part that gives us the information that we have the ester. So if you take a look at the second picture I posted, you'll see the carbon one. That's the hint that we don't have a pure aldehyde. So because we see that we had that peak at 160, not at 200, where we would expect an aldehyde to be. But if we look at the first picture, we see that we see aldehyde protons around 9-ish. The proton that's on the aldehyde carbonyl carbon, that one shows up around 9. We had, 8.2 or something this time. So sometimes there is a little bit difference, which is fine. But something that you don't typically see, you're not going to ever see an aldehyde at 160 in carbon NMR. So that's pretty indicative that we have the ester. And since from IR, we knew that we had a carbonyl, we knew we had no OHs, so no carboxylic acid, no alcohols, but we did know that our options therefore were ester because we had 2 oxygens. We either have an ester or an aldehyde ketone and an ether. And since our carbon NMR shows that we do not have an aldehyde or ketone, we must have an ester only as our option here. So that's going to take care of both of our oxygens in our chemical formula. And so then the rest is figuring out the carbon and hydrogen pieces of it. Does that make more sense? I know it's going to take time to reference these values.
That makes sense.
Okay. Good. So let's just take a look at the rest of this, and then we can look at some more. So we have 2 triplets here, and then a sextet or quadruplet, depending. And that one we'll have to make the determination later. But for triplet, that'll be a little bit easier. A triplet, remember, means it's next to CH2, or two hydrogens, right? So so we have a triplet at 4.15. We know that stuff adjacent to esters would show up around, next to oxygens would show up around that range. So that tells us we have, I'm going to just copy it. So we have the triplet at 4.15 with 2 hydrogens there. We know that considering we already have that half of our molecule done, that tells us we have a CH2 next to our oxygen. Because that's what we're going to see at 4.15. And we see that it's worth 2 hydrogens from the integration. And it's a triplet, which tells us we have another CH2 next to it. So this triplet here tells us we have 2 hydrogens nearby. So that must be another CH2 that's adjacent to that. So using all the bits of information, we can deduce, at least so far, this part of our molecule. Kevin, by the way, we're doing number 2 on the spec sheet. All right, so Shane, does that make sense how we can figure out this part? So this part we got from carbon NMR and IR, and we used the proton NMR. We had that aldehyde from the HNMR. So that part we've taken care of. There's nothing else that can go on that part because we have no more place to make bonds. Right, so aldehyde is a terminal. It's got to be the end of a molecule. So with this, we see, okay, we've got a triplet at 4.15 worth 2 hydrogens. So that means it's a CH2 that's next to our ester. Because we see we have nothing else that's really high up, chemical shift-wise. The rest are just alkyl substituents. So that's going to be the part next to our ester is a CH2. And because it's a triplet, that tells us we have a CH2 nearby. Its neighbor on the other side is CH2.
So I get why you can see that there's another CH2 on it. But how do you know that triplet at 4.15 is a CH2?
Because of this. Because that's worth 2 hydrogens.
Oh, I see.
From the integration.
Oh, I see, because the integration.
Gotcha. All right, and then we have this last 2 bits here. We have the sextet or quadruplet, and then we have another triplet. And that triplet worth 3 at 1.0, that's a methyl group, right? I mean, we don't even need to look at the fact that it's a triplet. It's worth 3, it's at 1.0, it's a methyl group. So since we only have 1 carbon and 3 hydrogens left in our formula, let's go ahead and see if that's all it is. If we see that, yeah, we're expecting this, therefore, to then be, yeah, that should be a triplet at 1.0 worth 3 hydrogens, and that's indeed what we see for our thing. And then we see that we have, therefore, 5 hydrogens. We have 5 hydrogen neighbors to this middle carbon, and so that would mean that this should be a sextet. And indeed, we see a sextet worth 2 at, what was that, like 1.7-ish. And so we indeed, this is a very likely candidate for this molecule. And we don't really need to even look at the rest of the carbon NMR. I mean, yeah, we have 65 that's something next to an oxygen, and the 10 and 20 are kind of useless. So, therefore, this should be the molecule that we're looking at here. And I totally understand this will take more time for you than it does take right now, me going over it. Which is why you're only going to have like 2 of these or 3 of these on your exam. So, because it's going to take so long. So it's all a matter of... go ahead.
Yeah, so... I mean, this all makes theoretical sense.
Would you be able to do it? That's the question.
For me, I can kind of get the puzzle pieces, but then figuring out what the exact structure is.
Yes,
is challenging.
I agree. That is the hardest part.
And then I just don't know how to confirm it.
Yeah, so confirming it at that point, I would go back to the notes and be like, okay, well, we're expecting. If this was our product, this is where we would expect all these peaks to be. And so we can do that right now. Let's take a look. So if we had this molecule, and I'm going to draw the H's in. First of all, like the most basic things we would do is we would see IR, we would have C double bond O, and that's it. That's all we would see in IR. With NMR, proton NMR, we would see 4 signals because we have 4 different types of hydrogens here, right? So we can look at the most basic things first. Like, if we have 5 signals in our spectrum, I don't have the spectrum here. Why am I scrolling up? If we had 5 signals in the spectrum, then yeah, that's a problem. But well, we're looking at this, and then so we'll go ahead and then now look. We'll see. Okay, well, let's look at this proton. This proton, we're looking for around 9 ppm, 1 hydrogen, and it's always a singlet for an aldehyde. for this one, we're looking maybe if we follow the like mathematics that I gave for like things next to oxygens or whatever, I think you get 4.3 ppm for next to an oxygen. We'll see it's worth, integration should be 2, and then it should be a triplet. The hardest part is the chemical shift, right? Yeah. And so that one, it's best to then look at the notes and be like, well, something next to oxygen, we're looking, it's a CH2 next to an oxygen. I think that's on my other tablet, so I can't just swap over to that, but I would have the notes there. You can just reference the like kind of little chart we did of calculating chemical shifts, and that would be how you can confirm it. All right, and then for the next one, for this one, we're looking, so remember that 1 carbon away, so directly adjacent to oxygen is like, I don't know, what, 2.5 or so that you're adding on. 1 more carbon away from that is about 0.5. So we're looking at about like 1.6, 1.7 ppm for this one. We're looking for it to be 2 hydrogens. And we're looking for that one to be 1, 2, 3, 4, 5. This should be a sextet. And then if we look at the last one, that's just a plain old CH3. So that should be 1 ppm, 3 hydrogens, and that should be a triplet because it's next to a CH2. And that's it. And then carbon NMR. So are those H predictions okay without the ppms at least?
Yeah.
Okay, cool.
That makes a lot of sense.
Yeah.
Cool.
That makes a lot of sense.
The carbon NMR, we would expect something around between 150 to 200. We're also going to see 4 signals because they're all different carbons. We're going to see something between 50 and 100. And then we're going to see 2 things that are less than 50. So carbon NMR, you really have just like 5 regions. Above 200, 150 to 200, 100 to 150, 50 to 100, and then less than 50. So it's just chunks by 50s, right? So we see that we have, in this molecule, our carbonyl should show up around 150 to 200, generally on the lower end of that. We have a carbon next to an oxygen. Those show up between 50 and 100. And then we just have 2 plain old regular aliphatic carbons. Those show up just less than 50. And since they're not identical, we're going to see 2 peaks there. 2 peaks below 50. And so this is kind of our confirmation of this. And like if we were to try and put this together a different way, we would see our confirmation would not line up. If we were to try and say maybe we did this way, this would be we just move it would be an aldehyde and ether, so not an ester. IR we would still see the same thing. Go ahead.
So that carbon between the oxygens would be
the oxygens
this one would probably be about
higher.
like 4.7 or 5.0, somewhere around there. We would see 2 hydrogen singlet because there's no neighboring hydrogens. Aldehyde hydrogens don't split things. We would still see, by the way, our 9.0-ish singlet, 1H.
Mm-hmm.
And then if we look at here, we would say, well, this is going to be around 3.8. And that should be 2 hydrogens, and it'll be a quartet. And then this one will be like 1.5 maybe. 3 hydrogens, and it would be a triplet. So the big part is here, you would see a singlet. That's the big part that tells you this one is wrong.
Gotcha.
Because in our spectrum, we have no singlets aside from the aldehyde. And then indeed, in the carbon NMR, you would see a peak at 200 plus. You would see one at probably, you'd see 2 peaks between 50 and 100. And you would see 1 peak below 50. So the big things that are here is our chemical shifts. We would see two things in the kind of upper ranges, and we would see a singlet there. And so this is not going to be the case. And then for Carbonatomar, we would see one of those down below peaks would be shifted up. So let me take a look at the... let me move that spectrum over here, and let me start sharing that one. Okay. So because you see here we have one peak between 60 and 100. That there, by the way, is chloroform. That little blob, we don't really ever worry about that. That's not really a peak. So we would see two peaks between 50 and 100, and we would see something at 200 or above. If that was our second molecule. And then, again, we would see something higher up here. In fact, what am I doing? I can just show you what the spectrum for this other molecule would be. So we can see if our prediction is correct or not. Give me a sec to make it. And then, let's see. Oxygen, hydrogen, oxygen. Okay, so if I take this molecule, and let's predict its proton NMR shifts. So, how can I? Okay, so I'm gonna show you this screen. I don't think I should. Yeah, I will. Okay, whatever. Okay, so if we go ahead and estimate what this molecules would be, we would see something around 9. Again, we're seeing this 4.5, 3.5, and you see ideally this should be a singlet. It has it split by the aldehyde proton, though generally that's not something we'll see except with a very, very fancy instrument. And then indeed we see a quartet and a triplet for the other sides of the molecule. And then if we were to take this and do a carbon NMR, indeed we would see something 200, two things between 50 and 100, and then one thing below. So if this was our structure. So so indeed our predictions would be not the right ones here. So yeah, it's absolutely very valuable to still have your like if you can do your double checking. Definitely a valuable bit there. Okay. Oh, I forgot to put these in my recorder. So this would be our carbon NMR. We'd see all these crazy high up peaks. And then the proton NMR, I've deleted it, but let's go back and do the proton NMR. There it is. And so, yeah, we see everything up here. We don't see the two peaks we had down in the one region-ish. So, there we go. Okay, so that was all the ones that I had coming into this, which unfortunately took a lot of time, but that's okay. It was hopefully still useful. Shane, do you have questions you'd like to go over?
Not specifically.
It's the same questions,
yes.
Just the spectra
okay, and
questions.
Let's double check with the answer key, just making sure that I'm not completely wrong here. Let's see. Oh, it's a JPEG. Okay, propyl format. Yeah, we're correct. Okay, good. So we indeed got the correct structure here. So we have time. Let's do one more. Choose your favorite, 1 through 25.
So I'd started working on all.
Up through 13,
so maybe
and
14 or
so
above.
maybe like
right.
14 or above.
But for all these, I've gotten to the point where.
I start with the IHD,
I look at the IR
and then I look at the IR spectra to see what I can find, which
more or less successful there.
more or less successful there.
I think I've been
confusing myself with the spin-spin splitting.
As far as
when it does the complex
Only
splitting.
really worry about that
and
with,
when it's just
with aromatics. Or unless you're talking about like doublet of doublets, that sort of thing happening. Okay, yeah. So that's only going to happen with vinyl things. And again, sometimes you'll see it, sometimes you won't, because it depends how good your NMR instrument is. So because I'm using software to generate mine for the exam, it will have the most like perfect splitting of all. So you will see that sort of thing. So like you're talking about problem 12 where you have this. Okay, so that's not going to happen on our exam. We're not going to have like extra weird splitting happening. No long range coupling.
I guess I was under the I was under the impression that, say it's a CH2 with carbons on either side that have hydrogens on them. I thought there was going to be complex splitting regardless, but it seems like it's simpler than that.
If everything is just single bonded, it's very simple. It's only when you have double bonds that things get weird, and that's usually just because of geometry.
Oh, that
makes it less confusing.
Good.
That makes it less confusing.
And then I guess I'm just not.
Utilizing the chemical shift as much as I should.
And so again, there is still a range with chemical shifts, but they're not absolute values at all, right? So there's still a little bit of variability here. So okay, let's see. Let's take a look at. This one should be fun. Okay, let's look at number 16.
Okay.
All right, and then I have to let me open up the formula. Formulas. Okay.
I have it if you.
Oh, cool. Yes,
I have it if you want.
C4.
C4H6O2.
Really? I thought there would be nitrogens looking at that spectrum of the. Oh, okay. Never mind. Those are just carbon hydrogens. Duh. Okay, let's take a look. So IHD. Will be 0. No, 2. I don't know how to calculate. Like, wait a second. No, it would have to be 10 hydrogens for that. So we have IHD of 2, right? Yeah, cool. Okay, good. I don't have to go through that. So our IHD is 2, so we either have 2 double bonds or 1 double bond in a ring. Those are our options. Or 2 rings, I suppose. Though with 4 carbons, that's pretty unlikely. So
yes.
Yes. I don't know.
You want me to just stay here quietly?
I don't know if you want me to just stay here quietly or.
No, don't. No, by all means.
But I mean.
Yeah.
In my mind, there's IHD is 2. There's 2 oxygens.
And not that many carbons.
So I'm thinking 2 double bonded oxygens.
And then looking at the IR spectra,
it looks like there's the C double bonded to O.
And that's about all I see.
And that's about all I see in the IR.
That's all I see as well. So. Useless. Okay, next. So let's consider this. So I have written here on my notes, we either have a ring and a double bond or 2 double bonds, and this might be C double bond O's. So we might have that. We might have an ester as well. Remember, 2 oxygens could be an ester, could be a ketone and an ether, or in this case, could be 2 ketones or 2 aldehydes. So let's take a look at NMR. So what do we see there? Let's write down our peaks. So on the NMR we have, what is that? 3-ish? 4.3 ppm. We have a triplet. That's worth 18.92. We have at 2.4. That is another triplet. And that is 19.77. So those are about the same, right? 18.9, 19.7. Those are about the same. And then we have, again, what is that? Probably a quintet. Yeah, looks like a quintet. Again, some of the multiplicity is hard to see. And you might have to then look at your structure and be like, oh yeah, of course it's a quintet. So obviously, though, it's not like a triplet, and it's not a doublet, it's not a singlet, right? So it's probably a quintet. Though it's a little bit harder to see. Though again, my exam ones, it will be very obvious, and I will zoom them in as much as necessary. So, okay, so this is 2.2-ish. We have a quintet, and also worth 19. And so, since we have 6 hydrogens, these are all the same. These would be two hydrogens each, right?
Yep.
Cool. Okay. And then let's look at carbon. We have something at 175 or so. 65. Maybe that's 70. I don't even know. It doesn't really matter. And then we have 2 peaks below 50. So we have one at like 28 and one at 20. Cool. So no symmetry. We have 4 carbons, 4 peaks, no symmetry then. All right, go ahead. Talk to me. What are we going to do here?
Well, at this point, are you going to look at the number of peaks and try and see what's next to anything, or are you just...
You can, yeah.
Well...
So what's curious here is, notice we have only 2 hydrogens for all of our things. So what does that tell you?
CH2s.
Yeah, what is the... Yeah, so they're all CH2s, which tells you what?
So maybe there's an oxygen on either side.
Could, yeah, could be.
Probably a ring.
So what might that look like? Or yes, that's the other option there. So but mainly that what you're both saying is, though, we have no CH3s.
Right.
As we have no terminal methyl groups. So it's either we have heteroatoms at the end, or we have a ring. Right? So a ring doesn't have a terminal, a terminus. There's no methyl group that would be at the end of a ring. And so then we'll look at the IR. We saw we did not have any OHs, right?
Yes.
No
Those
OHs.
would be
So
above
therefore
3,000.
we don't have oxygens at the end either. Yeah, we would see a blob at 3,000. Like what's a good example of that? Like number 20 would have an OH for sure. Like if you scroll down to number 20, you should see an OH in that one for sure. Yeah. Very obvious. And so we have no OHs, so that means we don't have something that has... We don't have something like this.
Mm-hmm.
Right, and obviously this other one, like we there's no OHs in this molecule, so it's got to be a ring then. So since we don't have any CH3s, we don't have heteroatoms on those carbons, it must be a ring.
Wait, how do you know that there are no heteroatoms?
No heteroatoms at this side, because if we have our 4 carbons, 1, 2, 3, 4, because we have no CH3s, we would have to have something like this. And in fact, that's 4 things. So like if we just tried to make this work out, I don't even know, we'd have an H here or something. Like we have no CH3s in this thing. And that's hard to do with a linear structure. Linear things almost always have CH3s unless they have like a primary alcohol like this. But we know we don't have a primary alcohol because we have no alcohols at all. So there's like not another way we can make this work so that we don't have CH3s unless we have a ring.
I don't see any evidence of sp2CH stretching. Nothing above 3,000. There's nothing around 9 aldehyde.
True, we don't really see that either, but the aldehyde would be the more giveaway. Yeah, we don't see any aldehydes here either, right? We have nothing at 9 or 8 ppm for proton NMR. So, as a result, the only way to have only CH2s is to have a ring. Like, if you think cyclohexane, every carbon in cyclohexane is CH2. We have no CH3s. So, that's going to be our hint that we have a ring here. It's going to be very hard to make a linear structure without CH3s involved. Unless you have aldehyde and other things, but we don't have any of that. So, like, technically, with how many carbons? 4 carbons? This would be the only way we could arrange this with no alcohols and no CH3s. But we see here we only have 2 CH2s. And then we would have 2 aldehyde peaks. And then this molecule is also symmetric, so we would only see 2 peaks in carbon NMR as well. So can't be this either. So our answer then must be a ring. So we have to have this is either we've either got a 3-membered ring and some other like weird, I don't know, some weird thing like that. We could have a 4-membered ring. Maybe we've got 2 ketones. We can't have 2 ketones because our IHD is only 2. So one of them is taken by the ring, the other is by this, and we have no way of making an OH, right? If we have no H's and we can't make a second carbonyl, so we know we have no OH because of the IR. And we can't have 2 carbonyls and the ring because our IHD is only 2. Remember, a ring would also take one of your IHDs. So that means that oxygen must be part of the ring. We have to have an ether. Ethers don't show up in IR, so we don't see the OH. So we have several options then. We either have this structure, or we have this structure. So it's still a 5-membered ring. In either case, 4 carbons in there. 4 carbons in both rings. So these are really the only 2 options we have.
Sorta.
Does that make sense, Shane?
Sorta.
I know we're going
So
fast.
the
and there's
4-member
so much
carbon
information.
square, that
So
wouldn't happen because would
yeah,
those
go
2
ahead.
carbons be more similar?
Carbon square.
The two,
That
like the
wouldn't
top 2
happen
carbons.
because would those 2 carbons be more similar? The top 2 carbons.
Not necessarily.
Right,
This
okay.
is the main reason we can't have
But I guess just
the 4-carbon square.
on the
Is because we don't have any
again on that
OHs.
square,
We have to figure
would
out where to
those
put
top
that
2
oxygen.
carbons be closer together on the C
Again,
NMR?
on that square,
Mhm.
would those top 2 carbons be closer together on the C NMR?
Okay.
I'd say so. They would both be pretty similar. Yeah, they would probably be. They would. I mean, but in our current carbon NMR, we have 28 and 20, so we already have 2 similar ones. So we're looking at. Oh, by the way, also this tells us we have no ketone. Right, ketones are always above 200. So. Right. Well, I'm sorry. I might be going ahead of myself, Shane. So, so do you see why these are the only 2 options so far?
Yeah.
Cool. So we know that this one is a ketone plus an ether. This one is an ester. And we're going to see that this is going to be the correct structure, and we have several reasons for that. Not only do we have no carbon peaks above 200, which is where ketones would show up. So this can't be right because we have no C above 200 parts per million. But we would also expect this to be a singlet, right? That one has no neighbors. And here we would have triplet, triplet. And if we look at our things, yes, triplet, triplet, but that's not a singlet. So we don't even have to look at chemical shift, just look at multiplicity. And so, and also like triplet, triplet, quintet, that's CH2, CH2, CH2. Right? We have one CH2 that only sees 2 carbons. We have another hydrogens. We have another CH2 that sees 2 hydrogens. And then we have one CH2 that sees 4 hydrogens, which is the quintet. So, we have a lot of reasons why that molecule on the right is not the correct structure. And then if we look here, we're expecting this one should be a triplet, this one should be a triplet, and this should be a quintet here.
Carbon 2 will be
because we
higher
have 2
on the
carbons on each
scale.
of them. They're all CH2s. And so,
I see.
go ahead.
Like a shift of
higher on the scale.
4 is like a shift up of 3 ppm.
Directly.
Oh, I see.
And that's what's that? Go ahead, Kevin.
4 is like a shift up of 3 ppm.
Yeah, about 3 ppm, right? So, and yeah, so we do see 4.3 here. So this one will be the one that at 4.3, and this one will be the one at 2.4, and then this one, the only quintet, right? So the quintet is the one at 2.2. So, all right. So and that's what we're looking at here. So yes, lots of work. Lots of work. And so there's so much. Yeah, I mean, like, yeah, you can figure out the pieces, but assembling them all without practice is really tough. That's the hardest part, is assembling it. And so that's the thing, is like, of course you'll get partial credit if you submit this as your answer for this one. Like, yeah, you'll get partial credit because you've the more work you show, by the way, also the more partial credit. So even if you don't even get the final structure and you get all the pieces, that's most of the work. So like you can at least scrape by for whatever that's worth. So yeah. By the way, also it's always a good idea to, I'm going to ask you to do this on the exam, is to take your peaks, label them A, B, C, and draw them on your thing. So you'll say like, these are hydrogen A, these are hydrogen C, these are hydrogen B. And then like for the carbons, you'll also do that. You'll say like A, B, C, D. You'll say A is your carbonyl carbon. I'll do these in a different color. Red. Carbonyl carbon is A. The one next to the oxygen is going to be the one between 50 and 100, so that's B. Let me rewrite these here in red. A, B, C, D. And these ones, again, the 28 is going to be kind of probably the one next to the carbonyl. And then D is the one that has the least amount of deshielding going on. So it's a good practice, because this way it's going to force you to double check back to your thing. So on these spec problems, it would be a good idea to label on your final structure which peak corresponds with which hydrogen.
Yeah.
And that'll help you.
That's good to know that that's worth
kind of
credit.
Conceptualize it as well. All right, so like, does that make sense what I'm trying to say?
Yeah.
Cool.
And that's good to know that that's worth credit.
Yes, that will be worth it as well.
Yeah.
So, I mean, I can give you a practice exam, but it's really exactly the same as these things.
Yeah.
So, I can show you what that'll look like question-wise, but really, it's like, here's a spectra, give me the structure, show me all your work. So, I can put that up later.
It's better than nothing.
Well, hopefully this was at least a little bit useful.
No, this has been helpful.
To help get you going, and
it's better than nothing.
Better than nothing, right? So.
Oh, I heard back, and they're okay with
good. And I know Kevin
Discord like this.
Tomorrow. Did you decide, Kevin? Is it going to be Zoom or?
Sure. Oh, I heard back, and they're okay with Discord like this.
Okay, cool.
Oh, you'd also see.
If you want, I'll ping everyone right now.
Higher peaks, if you had like more carbons, like you had an isopropyl group, you probably able to tell on the CMR which was the two methyls on that methine carbon. If you had like carbons, like an isopropyl group. This is why I saw it from some videos online. Which was the two methyls on that methine carbon.
Yeah, probably.
This is why I saw it from some videos online.
Generally speaking, but usually the isopropyl is really easy to see in Proton and NMR, because you see two doublets worth 6 hydrogens, and then a quintet. I'm sorry, a 6 plus 1, 7 septet in worth 1 hydrogen as an isopropyl group. They're really easy to see in Proton and NMR as well. So they're usually very easy to detect. Okay, so Kevin's review is 3 to 4 p.m. tomorrow here on Discord. Alright, so that should help with that. And then, definitely, Shane, I would take a look at those general chemical shifts for proton and carbon NMR. These are, again, ranges. You may see things that exceed these a little bit, but they're pretty standard. Like, you really don't see aldehydes and ketones below
Okay.
200. And if you did see them below 200, it would be like 195. You're not going to see them at
Yeah.
160. So, like, usually you can rely on these pretty well. Okay? So, that'd be good, I think. Print these out, stick them to your head. Some of these chemical shifts on the proton aren't all there. Like, they don't have everything.
Right. I think the
so
hydrogen on the carbon side of an ester is like around ppm of 8 or so. There's not a lot of information on that, but
okay.
Right. I think the hydrogen on the carbon side of an ester, I think, like around. There's just like a. It's not a lot of
For an
information.
ester,
Yeah, aldehyde ester.
The side of ester is usually 4.3. That's usually pretty indicative.
I think.
Unless you mean an aldehyde. Aldehyde ester.
Yeah, aldehyde ester.
Yeah, those will go a little bit down. Yeah. Just because the ester is resonating, so you do end up having a little bit more shielding, because now you have the ester oxygen contributing electron density, which helps to put more electron density back in the hydrogen, so you end up shielding it a little bit more. So, but that's a little bit more, advanced. Okay, I'm gonna go